Thank you. It's a great pleasure for me to have an opportunity of giving a talk here. I will talk mainly about the dynamics of the liquid crystals. But today's lecture is not not on the liquid crystals, but it is rather it's a general scheme. I will talk, and today's talk is an introduction of what I am going to talk tomorrow. So it is a Brownian motion and viscoelasticity of Rodlike polymers in isotropic solutions. Let me first explain. So this is the structure of my talk. First, introduction, and then I will explain this principle, Onsager principle, that is quite useful in deriving equations in the dynamics of various phenomena, various non-equilibrium phenomena taking place in polymers and colloidal systems. And then I'll discuss about the viscoelasticity in isotropic solutions. Introduction. Somehow, never mind. This is nuisance. Excuse me. Why do I have this one? I think for those, and I don't have to explain about the liquid crystals. Here I will talking about the simple liquid crystals, nematics. So that I consider the small molecule as the rod-like molecules, and they can be small molecules, and that is used for displays. But the material that I'm going to talk here is mainly a very long rod-like polymers. This is a polymers, and these are the materials that are used in Kevlar as the bulletproof jacket. Yeah. So they typically the size about the 1,000 nanometers, 1 microns, and so it's a very so the relaxation time of this material is very long, so it's typically a millisecond to second, and therefore I think you can actually see the the relaxational behavior, the molecular relaxational behavior, and which that I will come shortly. Now the rod-like polymers have, depending on the concentration, you have these structures. If the concentration is very small, you have a dilute solutions where individual molecules can move around independently of each other. If we increase the concentration, you will have this situation where the polymers, they are hindering each other. So if one molecules tend to rotate, it hits on the others, and therefore the rotational the relaxation takes place very slowly. This is still an isotropic solutions, but that is quite different. The solution behavior is quite different from the solution behavior of dilute solutions. And if you further increase the concentration, you will have the liquid crystals. And theoretically, you can show that the Onsager showed that if the length of this rod is big L, and N stands for the number density, number of polymers per unit volume, if this condition is satisfied, you will have this situation, dilute solutions. And if NL cubed is larger than 1 and still less than certain critical value that is determined by the aspect ratio, the ratio between the length and diameter of the rod, you have an isotropic solution. And if this concentration exceeds these conditions, you have an allotropic nematics. And but today I will mainly focus on these dilute solutions. Now, I have to explain this keyword, viscoelasticity. Now, this polymer is a very large object, and therefore it moves very slowly. And so if so, you will have this so this is you will have this property called viscoelasticity. It is basically a viscous liquid, but it has elasticity. So these are the kind of examples of the viscoelastic liquids that you see, like an bubble gum. Yeah, I think chewing gum, where it is a liquid, but it behaves like an elastic material, like rubbers. So if you stretch it and then release it, and it is stretched, but it tries to shrink back. So it is an elastic liquid. And so these are the characteristics of the polymers, and they are mostly they are mostly the properties of the long flexible polymers. But it is known that the Rodlike solutions of this Rodlike object also show the same behaviors, viscoelastic behaviors. It is a liquid that has elasticity. So you can actually measure the elasticity of the liquid by the following way. So you have this sample, and you sandwich your sample between two plates, and you put the weight here, and if you put the weight, you actually shear the top plate, fixing the bottom plate, and then this, due to the gravity, and this top plate slides, and if the ratio between this displacement divided by the gap distance is called the shear strain, and the force acting on the unit area on the top plate is called the shear stress. And if this is a purely usual Newtonian fluid, like water and alcohol, the shear stress is proportional to the shear rate, and the ratio is this constant is called the viscosity. So if here I am considering the following experiment. So I put weight here, then then this gamma dot is constant. So if we put a weight here, so the shear stress sigma is constant, and therefore gamma dot is constant, and therefore the shear strain increases linearly in time. So for the Newtonian fluid, this is the behavior of the Newtonian fluid. So the shear strain increases, so just the plate starts to move with constant speed, and at some time t naught, if we cut the string here, then we set the sigma equal to 0, and at that time for the Newtonian fluid, that the top plate stays there. But if in a viscoelastic liquid, since it has elasticity, when you stopped pulling this top plate, then just the top plate just retract to a certain extent. So it is an indication of the elasticity. It is an evidence of the elasticity of the liquid. And this kind of viscoelasticity is important in polymers, and also important in liquid crystalline polymers. Now, why do we? Okay. I think I will skip that point. So one of my main aim of this talk is to explain to you why such phenomena, why the liquid can have elasticity. Now, what is the origin? Let's see whether I can explain this to you. So why the liquid crystalline, why the Rodlike solutions of Rodlike polymers have such an elasticity? And the explanation is the Brownian motion, the rotational Brownian motion. This these molecules, Rodlike molecules, are just doing Brownian motion. It is doing translational motion as well as rotational Brownian motion. And it prefers the isotropic state. Okay, but if you share it, if you're sharing the solutions, these rods are oriented, but it is not the happiest state for the polymers. They want to go back to the isotropic solutions. And if you stop shearing, okay, or if you release if you set the shear stress equal to 0, then due to the Brownian motion, okay, they just move around and tend to recover this isotropic configuration. And during this process, it just puts the top plate back, retract. It makes the retraction of the top plate. And I can show you that in this case, well, I think this is I'll derive this formula later, but it can be shown that the shear stress of the solution of Rodlike polymers is directly connected to the orientational order parameter, where U is the unit vector parallel to the molecules. So shear stress is a direct indication connected to the orientational order parameter of the Rodlike polymers. I will derive this is sort of simply a physical explanation, but I will give some more detailed derivation later. I also because the polymers are large molecules, and because the relaxation time is so large, so the nonlinear effect is important, can be important. So for the pneumatics or even for the isotropic solutions of this Rodlike polymers, the viscosity is not constant. It actually changes with the increase of the shear rate gamma dot. And typically this can be changed tens or some orders of magnitude. The viscosity decreases by that factor. So the thing I want to do here is that how to deal with the viscoelasticity of the solutions of Rodlike polymers, and how to derive the basic equation that governs the phenomena. All right. Then let me move on to this to the topics, the Onsager principles. This is a principle that Onsager proposed in his celebrated papers, in his 1932 papers, in which he proposed the reciprocal relation in the irreversible thermodynamics. And but I explain. I do not give the general explanation. I only give you try to persuade you what is taught, what is the essence of this principle. For me, I think it's quite easy to understand the Onsager principle in this particular example. Let us just think about the systems or particle systems moving in a viscous fluid. Okay. So suppose that you have some sand particles are falling in a viscous fluid. Okay, and of course this is a non-equilibrium process, and so the state of the system can be described by a set of parameters. So the x actually x1, x2. This set of parameters describes the non-equilibrium states for the particle configuration. If you are just considering just the sedimentation, the falling of one particle, this can be the position vector plus the orientational other three variables. And if you have many particles, you have a set of such the generalized coordinate, let's say. And so these particles are moving around in potential under the influence of gravity. There is a potential energy that is a function of x. Now, in this slow limit, if the inertia effect is negligible, and which is indeed the case in the polymers in the colloidal systems, the inertia effect is very small, and therefore we can derive the time evolution equation of the system by the force balance equations. And this stands for the force. This is a general form of the force balance equations. du dxi is a force, u is a potential energy, and therefore its partial derivative stands for the force as a potential force. And this potential force, of course, this potential force drives the particle to fall down. And this is the frictional force. If the particle moves in a viscous fluid, it experiences a frictional force from the fluid. And this frictional force is proportional to the velocity. So in the case of the spherical particles, this is simply the Stokes formula, 6 pi eta a times the velocity. And if there are many particles, I think this is in general this is written in this form. Now, a very important thing here is that this coefficient theta is called theta ij is called the friction matrix, and it is very important that it can be shown that this frictional force is symmetric. Theta ij is equal to theta ji. Now this can be proven. I'm not going to, but this can be proven if you start from hydrodynamics. If you we know how if you use the hydrodynamics, Stokeskian hydrodynamics, we know how to calculate this friction coefficient, and from that you can prove this reciprocal relationship. Now, the beauty of the Onsager's theory is that you can actually prove this kind of reciprocal relation without using hydrodynamics. Onsager used this Einstein's idea of that this frictional coefficient is actually related to the time correlation function of the random force acting on the particles, and since the time correlation and also since the time correlation function, since the fluctuation taking place at the equilibrium has this time reversal symmetry, you cannot the Brownian motion you see in your video. Suppose that you take a Brownian motion of particles and take a video, and suppose that you show it to the audience in a reverse mode. The audience cannot tell whether you are showing it in the normal mode or the reverse mode, because both the normal the phenomena, the process in the normal mode and the reverse mode can take place, are both allowed by the principle of mechanics of the physical principle, and also you can prove that it takes place. The both phenomena takes place with equal probability, and this is what is called the time reversal symmetry in the fluctuations taking place at equilibrium. And by using this very general principle of physics, he can prove this reciprocal relationship without using hydrodynamics. So this is a very general principle. And in a general way, one can say that this time evolution equations is actually indicates the following. Suppose that this x stands for some set of x now stands for a very general set of parameters that varies slowly in time. So we call it a slow variables. And in this case, the slow variables are, let's say, the position and orientation of individual particles. The other variables are, for example, that the coordinates, the velocity and the position and the momentum of the fluid molecules, they take place very fast. And these fast variables, the fluid molecules are moving much faster than the particles. And so if you have this clear sets of variables, so one variable changes very rapidly and the other variables change very slowly, you will have, it can be shown using statistical mechanics that the time evolution equation is generally has this form, and this friction constant theta ij is symmetric. And this principle, this reciprocal relationship can be set into this, and following following allows us to formulate the Onsager principle. This is a trivial change relating. So we consider this function, the theta ij xi dot xj dot is this is what we call the energy dissipation function. That is the energy dissipated in the system when the when the slow variables changes with the rate xi dot. And the second term simply stands for the change of the potential energy when this particle x, this set of parameters x changes with the rate xi dot. And you consider this a quadratic function of the xi dot, and this force balance equation is simply minimize this. I call this R the Rayleighian because the Rayleigh is the first person who introduced this kind of the formula. If we minimize Rayleighian with respect to x dot, and we have this time evolution equations. That's a trivially simple rewriting. And but what I'm going to do is that I am going to use this principle in deriving various time evolution equations for the non-equilibrium state of polymers and colloidal particles. And then there's the other convenient formula that is directly derived from the Rayleighian. Let me go back to this even more the simplest situation. One spherical particle is falling under gravity. Rayleighian in this case is given by this formula. Theta x dot square, this is energy dissipation. This is the first term is the energy dissipation function. And the second term stands for the change of the gravitational energy, mgx dot. And so if you minimize R with respect to x dot, you have a time evolution equation. Theta x dot plus mg is equal to 0. Now, now suppose that x is not the parameters. Suppose that x, you change the position of the particle externally. You put your fingers on these particles and move it. You control. You regard x as an external variable. You regard x as a variable that can be controlled externally by hand. So then the dr dx dot, this you can see that theta x dot plus mg, this is equal to the force that you need to apply to the particle to change the position of the particle with rate x dot. Okay, so this is just the sum of the frictional force plus this gravitational force. Now, in general, you can show that, so that if you have a radian x, and that includes some external parameters, p and p dot, then the force needed to change the external parameters is given by this formula. It's simply taken a partial derivative with respect to some external parameters. That gives you the force conjugated. That is what gives the force that is needed to change external parameters. Now, okay, I will show you the now here as an introduction. So I quickly show you two applications. One is the diffusion. Okay, so that the diffusion is a phenomenon that if the particle concentration is not uniform, the particle here will diffuse to the dilute region. Okay, excuse me. Yeah. And the set of parameters. The set of parameters x dot, that is the variables that specifies the non-equilibrium state, the current state. And of course, now this of course we can describe the non-equilibrium state by identifying the position of individual particles. But here I am going to describe the non-equilibrium state in terms of the number density of particles. NXT stand for the number of particles at position x. Okay. So our objective is to determine the time evolution of these number densities. Okay. So this is the same set of parameters. So the non-equilibrium state is specified by this function nxt, and our objective is to determine the time evolution of these state variables n dot. So we will construct the radian for this system, but since n dot has to satisfy this some conservation law, we need to introduce another auxiliary variable, that is the velocity of particles at position x. Vp stands for the velocity of the particles, and so if Vp is known, n dot is obtained by this conservation equations. All right. So now we will. I think. Okay. Now. Okay. So the free energy of the system can be easily written. If we know the density, density nx, the density of the system, the density profile of the system, the free energy of the total system is just an integral of this free energy density, kBt times n log n, this entropic term. So this is the free energy of the system, and therefore that this time evolution. Oh, okay. Excuse me. Now here, bear in mind that previously I used this symbol U to stand for the potential energy of the system, but in this general irreversible thermodynamics, I use the free energy of the system. So I fix the slow variables, and then we can define the free energy of that state where the slow variables fixed at x. Okay, so the AX is AA is the free energy of the system, and in the present case, that the non-equilibrium state is specified by the density profile nx, and the free energy is written as a functional of nx. So nx is the free energy is given by this way, and so therefore the a dot, u dot, or a dot, the driving force term can be calculated in the following way: simply that just take a time the n dot, then n dot can be expressed in terms of the Vp, and by using the integral by parts, we can show. So we have this, that a dot is given by this expression. So that's the potential energy term. The energy dissipation term is simple to obtain if the theta now stands for the friction constant of individual particles, and if the particle moves with velocity vp, theta vp square is the energy dissipation, and therefore this is the total energy dissipation taking place in the system. So this is radiation. And if we take the VP is determined by this Onsager principle, so that we can minimize radiation with respect to VP particle velocity, and that gives this simple formula. And this combined with this conservation equation gives you this diffusion equation, where the diffusion constant D is now given by kVt divided by this friction constant of a particle, the famous Einstein's relation. I can show you the other example. That suppose that this diffusing particles are confined by semi-permeable membranes. And we ask that suppose that you push this semi-permeable membrane in the flow solution and change the position of this membrane. What is the force? How much force you have to apply to this to these membranes? And once again, we can use the same principle. This is a radiation, but in this particular case, so this L. The position of the semi-permeable membrane, position of this membrane is an external parameters. And I write down the radiation explicitly accounting for this position of L. So that this is the energy dissipation function, the free energy term, and then plus, so this extra term comes from the integral pi parts. Okay, if you explicitly take into account of the position of the semi-permeable membrane from the integral by parts that are used in deriving this form, I have this extra term, and then just by differentiating this radiation with respect to L dot, I have an equation that is needed to change the force acting at the membranes, and that of course consists of the theta m is that I am assuming that some frictional the membrane's intrinsic friction constant times this second term stands for the osmotic pressure. This formula is applies even if the concentration is not constant. The osmotic pressure is this is the force. The osmotic pressure at the position of the membrane. This is the force that you need. All right, now, what I'm going to do, repeat the same kind of argument for the Rodlike, the orientational Brownian motion of Rodlike particles, and I'm just straightforwardly following the same kind of procedure. So now I'm going to discuss the rotational diffusion of Rodlike particles. Okay, so the rotational diffusion that the U is not constant, the vector parallel to the rod is not constant, it changes in time. And the orientation can be described by the two, one is using this an angular coordinate theta and phi, or some unit vector U. So the distribution function can be described by, I think I'm using the same symbol, the psi, theta, phi, t. They are normalized in this way. And also you can define this distribution function psi ut which is normalized in that way. And I will derive the time evolution equation for the distribution function using the Onsager principle. This is this is a bit of mathematics, but okay, let me go through. So this is a diffusion equation for the distribution function written in angular coordinate. Now psi dot satisfies this, and psi dot satisfies this conservation equations. And theta dot and psi dot phi dot are the velocity of theta and phi, the time variation of theta dot and phi. Now, if the rod rotate with this if the theta and phi change with this rate, or theta dot and phi dot, we can immediately calculate the, or maybe okay, this W should be 2 phi. We can immediately calculate the energy dissipation. Energy dissipation is equal to the some constant that is called the rotational friction constant times the square of the angular velocity omega. And the angular velocity is written in terms of theta dot and phi dot in this way. And so this is the energy dissipation function of the system. And the free energy of the system is again is obtained in the same way. Psi log phi entropic term, or this extra term you need because at equilibrium you have this equilibrium distribution functions. So this is a expression for the free energy term, and the rest is quite automatic. So this is a radian. This is the So from the radian you can just proceed. You obtain theta dot and phi dot from the or by minimizing this radian with respect to theta dot and phi dot, and combining it to the conservation equation. You have an rotation, what is called the rotational diffusion equation in the angular space. For this case, it can be written for this distribution function. The rotational diffusion. This is the rotational diffusion constant you have. It's slightly an elaborate equation, complex equations. Well, usually people define this psi tilde, this psi tilde is normalized in this way. And for this psi tilde, you have a more the rotational diffusion equation in this form. It may be more familiar for you, but actually they are the same thing. You can also derive the same thing, do the same thing for this rotational diffusion equation in a vector space, psi ut, and again that the principle is the same. The u dot, instead of the u dot, it's better to introduce this angular velocity omega. Then you can show the conservation equation now written in this way, but energy dissipation function, free energy is the same. And essentially, you get this form of the rotational diffusion equation, where R now stands for this rotational differential operator. Now, what I'm going to show you is that the Onsager principle is actually quite useful in deriving. It helps you developing calculations. This is a fairly deriving the diffusion equations in this angular space is it's a bit complicated object, but I think that the variational principle, you can use any variables and you can easily get the right answer. Now, you can extend this approach to the viscoelasticity problem. Okay. So the problem is that now suppose that your rod is not is placed in the place in in a flow field. Suppose, for example, the rod is placed in a shear flow. So the rod is now doing a Brownian motion in this in this shear flow. And so the okay, so I derive the rotational diffusion equation for the psi ut. Let's see. So the kappa is a macroscopic velocity gradient. This is an external parameter. In the case of shear flow, kappa is related to the velocity that you move at the top plate in the shearing experiments. So kappa is the external parameters. The time derivative of the external parameters, and you can calculate the energy dissipation function hydrodynamically. So now your rod is placed in the shear field, and so shear flow itself tends to rotate the rod with certain velocity, and it can be shown that this omega 0 is the angular velocity of the rod placed in the fluid. If there is no external flow, the rod will rotate with this angular velocity. And the energy dissipation function of phi is written in this way: omega minus omega 0 square plus there is some extra term. And in the dilute solution case, you have the energy dissipation. In the dilute solution case, the free energy is given by the same formula as previously. Now you can construct the Rayleighian, and you can derive the time evolution equation for the distribution function psi. So this is a Rayleighian from this the minimum conditions. You have this equation for omega, and this plus with the conservation equation gives you this the rotational diffusion equation in a flow field. And the other point is that given if you know the Rayleighian as a function of the external parameters, the dot of the external parameter, in this case it corresponds to kappa, the velocity gradient, the velocity gradient of the imposed flow. And this sigma alpha beta this is the macroscopic velocity, this is the macroscopic stress tensor, sigma alpha beta stress tensor. Sigma alpha beta is derived from simply taking a partial derivative of Rayleighian with respect to the velocity gradient tensor. And there is a bit of calculation, but there's no mystery, no secret. I mean, just straightforward calculation gives you this expression of the stress tensor. And you can show that the stress tensor depends on the orientational tensor of the rod, and plus there is some extra term here that is proportional to the velocity gradient. Yeah, and then finally that the last term stands for the shear stress by the viscous component, the solvent component, the fluid component. So for example, in the case excuse me, so this is wrong. In the dilute solutions, so let us explicitly apply. So I'm skipping the whole detail, but let us explicitly apply that formula to the case of the shearing flow, that the velocity is given by this formula, and where the gamma dot is a shear rate, and that is one component of the velocity gradient tensor. And for this case, that for the weak flow, this perturbation calculation indicates that ux uy, this component is proportionate to gamma dot, and you can show that this here's some rotational diffusion constant divided applied shear rate divided by the rotational diffusion constant gives you this xy component of the orientational order parameters. And if you plug this formula to the shear stress expression that I derived in the previous slide, okay, this is the expression for the shear stress. This term ux uy, if you plug this formula, you have an well, okay. I think okay, so this is a bit okay. This is essentially n theta. This essentially gives nl cubed times eta s gamma dot. This is the contribution of the rod. This is the contribution of the rod, extra contribution. The second term also gives the same order of magnitude. But in conclusion, that you will have that the if you put rod-like particles in a solution, the viscosity is higher than the solvent viscosity. It is higher because you have some obstacles in it, and these obstacles disturbs the smooth flow of the solvent, and therefore the viscosity of the solution becomes larger than the pure fluid, pure solvent. But the increase is not very large because you have this NL cube times the solvent viscosity term contributes this eta s gamma dot, and the contribution both times the contribution of the rod gives the NL cube times eta s gamma dot. Since in a dilute solution NL cube is small, is less than 1. The change of the viscosity is not large. And so the dilute solution is nearly a viscous liquid with small elasticity. It's basically just an usual. It looks like an usual liquid in a dilute solution. Okay, I think that's the. I think okay. I'm going to go to the end. No, but okay. Just to show you. If you go to the higher concentration in a concentrated solution, and in the in the pneumatic solutions, these things will be different. You can show that this time the contribution from the rod becomes much larger than the solvent viscosity, and it's the dominant term. And this is why you have a very strong, highly elastic liquid for the Rodlike solutions. All right, so that's okay, that part I'll come tomorrow. So this is the summary of my talk. I talked about basically two things. One is this Onsager principle. Onsager principle simply states that the Rayleighian constructs the Rayleighian. That Rayleighian is a sum of the energy dissipation function times the time variation of the free energy. And given this Rayleighian, if we know the Rayleighian, we know the time evolution of the system, and we know that the force needed to change the external parameters. And by straightforwardly by applying this principle for the rotational diffusion of Rodlike polymers, we can explain. We can construct the theory for the viscoelasticity of Rodlike solutions. Where this state variable is given by this distribution function psi, and you construct the Rayleigh as a functional of this distribution function. And knowing the distribution function, just following this principle, you get time evolution equation for the distribution function. You also have this stress tensor expression. Okay, and I do the same, repeat the same thing for the liquid crystalline solutions tomorrow. Okay, but there's no new physics. Just straightforward calculation brings you to this constitutive equation for the viscoelastic and liquid crystal. Thank you for your attention.